Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Thanks for joining us today. In this video we're going to be looking at binary addition. We're going to look at how we add the first digit in a binary number, and we're going to look at how we add together a digit that is somewhere in the middle of a binary number. And we're going to use two structures. One is called a half adder and the other is called a full adder, and we're going to look at how we develop the circuitry for these two structures. All right, let's get started. Binary addition, very important part of computer architecture. So we're going to first just kind of look at some examples of how we would add binary. And there's four situations that could occur. So 0 plus 0 is going to be 0. 0 plus 1 is going to be 1. 1 plus 0 is going to be 1, and 1 plus 1 is, sorry about that, and 1 gives us 0 with a carry of 1, that's 2. And so this is a carry digit, and so we want to be aware of that. Let me just highlight a couple of things here. So things of interest that we have in our additions are these guys here, which are the one digit that goes along the same sort of level as the digits we were adding, and this is what we call the sum. And then we have the digit here, which is what we call the carry. In this case it's a carry out. So it's carrying out to the next addition module. Okay, and then we have our bits to be added. And so typically, so in this situation where we are adding just the least significant bit, this would be A0 and B0. So these are the bits being added. Okay, so that is our setup here. So let's go ahead and build a truth table that goes along with this. Oops, I don't want to line. No, I just want to get back to black. Back to black, there we go. Okay, so what does the truth table look like for this situation? Well, first off, we have two outputs here. We have the sum output and we have the carry out. And we have two inputs, and that's going to be A0 and B0. So let's fill out the inputs, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And let's look at what the sums and carry out are going to be for each. So 0, 0, as we see in this first example, has a sum of 0 and a carry out of 0. And then 0, 1 has a sum of 1 and a carry out of 0. 1, 0 has a sum of 1 and a carry out of 0. And 1, 1 has a sum of 0 and a carry out of 1. So we can recognize that these are two of our basic gates. So the sum gate is an XOR, and the carry out gate is an AND. And so we can recognize that C is XOR, and S is XOR, and C is AND. So we can build this pretty simply. If we have A0 coming in to an XOR, that gives us our sum with B0. And then we have an AND gate where we have B0 and A0, and that creates our carry. So that's a pretty straightforward circuit to do an addition, which is cool. So we have the addition of the first two bits in a number, and this structure is called a half adder. It's only a half adder because what if you had a carry in? So in this case we don't have a carry in, so we can only use this for either one bit addition or addition at the beginning of a multi-bit number. Okay. Let's move the screen a little bit here. Okay. So the other structure that does deal with a carry-in is called a full adder. And so this one is needed for a possible carry in. And so that's going to be used for multi-bit addition. So let's look at an example of this. So we might be adding the numbers, say 0, 1, 1, 0, excuse me, and then 0, 0, 1, 0. So if we go through this addition, 0 and 0 is 0, no carry. 1 and 1 is 0 with a carry. And then 1 and 1 is 0 with a carry. And then 1 and 0 is just 1. Okay. So I want to highlight one of these structures as a total. And this is going to be the operation of the full adder. Okay. So let's bring this over here. So we have 1, 1, 1, 0, 0. And identify each of these structures here. So these 2 bits here are the 2 that we're adding, AN and BN. Right? This here is our carry in. This one here is our carry out. And this here is our sum for the nth digit. Now when I say nth, we have to track of what place we're in when we're doing this addition. And each of these adders is only going to apply to one place. And so when I have the n count, that's telling me this is n0, this is n1, this is n2, this is n3. It's the power, if you will, that associates with the place. And so in this case, we're looking at the 2 bits here. So this would be A2, B2, and then we'd have sum 2, we have carry into, we have carry out 2. Everything is associated with, carry in 1, because that's coming from the previous one, and then carry out 2, that's going to the next one there. So everything is associated with this column of the addition. Okay, great. So I'm going to move up here where we have a truth table and a couple of K-maps, and let's go ahead and build this out. So here we have X, Y, and Z, and actually I want to change these. So I'm going to change this to AN, BN, and this is carry in. Okay. And then our function here, we actually have 2 outputs. We have the sum at n, and then we have the carry out. So that is our truth table. So let's go ahead and build out the outputs here. So this is going to be 0, 1, 1, 0, 1, 0, 0, 1. And we can see this because the sum of adding 3 zeros together is 0. 2 zeros and a 1 is 1. 0, 1, 0, that's a 1. This is a 0 with a carry, which we didn't look at yet. This is just a 1. This is a 0 with a carry. That's a 0 with a carry. And that is a 1 with a carry. And so our C out here is 0, 0, 0. There's a carry. 0, carry, carry, carry. Okay, so those are our 2 functions, and so we can build them up in the Karnaugh map. So this is Sn, this is C out, and let's go ahead and write these in. So I got 0, 1, 1, 0, 1, 0, 0, 1. This one is 0, 0, 0, 1, 0, 1, 1, 1. All right, great. So first thing I notice here is that this is a checkerboard pattern. And because of our previous videos of looking at XORs, I can recognize that this is either an XOR or an XNOR. So I got to check if it's odd or if it's even. And so when I look at one of the rows with a 1, it's a 1, 0, 0. So that's only 1, 1 in the input sequence. So this is odd. So since this is an odd function, it can be an XOR. And so this is going to be represented by a 3-input XOR that has AN, BN, and CN as its inputs. So this is going to be SN is equal to AN, XOR BN XOR CN. Okay, so that's great because this is one gate, and so that's really a simple expression, a simple implementation of that expression. Cout is more of a standard Karnaugh map for us, so we're going to want to box some things. And so I can see there's a boxing of 2 here, there's a boxing of 2 here, and there's a boxing of 2 there. And so we get a Cout function that looks like this. We have so let's label these AN and BN, CN. Okay, so 1, 1 stays the same in this column, so it's BN and CN. And right here we have AN stays the same and also CN, so this is AN, CN. And this one, AN stays the same and also BN, so this is AN, BN. Okay, so this is our Cout expression. And up here we have our sum expression for the nth column. And one thing you'll notice about the carry out, we can think of this logically. When would you have a carry out? When at least 2 of your inputs are 1s, right? Or if they're all 3 1s, but you have to at least have 2 of them 1. So if we look at the expression here, it says, hey, if B and carry N are both 1, then we have a carry out. If A and carry N are both 1, we have a carry out. If A and B are both 1, we have a carry out. And so this is very logical and it makes complete sense. At least to me it does. So hopefully it does to you as well. I wasn't trying to say you didn't understand it. Of course that's what we're about here, is trying to get understanding. Okay, so let's build this then. So we have AN, BN, and CN. I'm going to have a 3-input XOR here. And that's going to get all of our inputs. So AN, BN, and CN. And so this is going to give me the sum term. And then I'm going to have a set of 3 AND gates. And they're going to feed into an OR gate. This is standard SOP format. And that's going to give me my carry out. Okay, and what comes into these AND gates? Well, first we have BN and CN, so BN, and then CN. And then we have AN and CN, so we can take an AN right here. We can take a CN. And then we have AN and BN, so we can continue with AN down here. And then we can take the BN from over here. Great. That looks pretty nice. So that is the circuit that represents a full adder, or implements a full adder. So we use this anytime we're in the middle of a multi-digit addition. And we can use a half adder when we're at the least significant digit. That's all we have here for this video. I want to thank you again for watching, and I hope you found value in this instruction. My name is Mike Stanzik, and this has been Digital Electronics Classroom. I want to remind you to subscribe to the channel and to like and comment as you see fit. I would love to see some of your comments. What did I miss? What did I do incorrectly? What do you want to see more of? What did you like? That kind of stuff. So, all right. Well, thanks again, and have a wonderful day.